These are notes for AP Calculus on the topic of Euler's method continued. So here it says the table below gives selected values for the derivative of function h on the interval from -1 to 3.5. See that? And it says h of -1 is -4. So that's giving you the point -1, -4 is on the function. And then it says using Euler's method with 3 steps of equal size used to approximate h of 3.5. What is the resulting approximation? So the step size, we usually call it delta x, if x is our independent variable here. And to calculate the what it's equal to, delta x, we just take first how far are the points apart. The starting point, which in this case is at -1, and where you're ending up, which is at 3.5. So we have 3.5 minus -1 divided by the number of steps, which in this case is 3. So that becomes 3.5 plus 1 is 4.5 divided by 3. Well, 45 divided by 3 is 15. So 4.5 divided by 3 would be 1.1. So our step size here is 1.1. Okay. So now once we figured out what the step size is, occasionally they'll tell you what the step size is, but oftentimes they'll just tell you how many steps there are. Then we can start with our starting point. In this case, -1, -4. Point here to start with. And the step, figure out the slope first, which in this case is the derivative h prime of x. Here we can just use the table at -1, when x is -1. You can see h prime is equal to 2. And then we multiply that by the step size, which in this case we just figured out as 1.5. And that equals, that tells you how much the y-coordinate changes. Change in the y, which is in this case our function h, is 2 times 15 is 30, so 2 times 1.5 would be 3.0, or 3. And then you add on the original y-coordinate, which in this case is -4, we had to this point. And that'll tell you, so this is how much the y-coordinate changes, plus where the y-coordinate was at that point, gives you the new y-coordinate. So 3 minus 4 gives you -1. So that's one time through Euler's method. And remember, it's 3 steps, so that means we're going to have to go through this process 3 different times. That's the first step. Second step here are to get our new x-coordinate, which is very important here. We take the other x-coordinate and change it by the step size, delta x. So -1 plus 1.5 gives you positive 0.5. And again, the new y-coordinate we just figured out was -1. And now we need the derivative at this point. So 0.5, you can see the derivative is 1 times 1.5 gives you a change in the y-coordinate of 1.5 this time. Plus the original y-coordinate was -1. Gives us a new y-coordinate, 1.5 minus 1 is 0.5. That's two steps. Okay. So now again, we increase the x-coordinate by the step size. 0.5 plus 1.5 gives you 2. We've got 2, and the new y-coordinate we just figured out was 0.5. At 2, you can see h prime is, the derivative is -5. Times step size 1.5. Well, 15 times 5 is 75. So this would be 7.5 and then negative. So -7.5 is our change in y. And then our original y-coordinate, we add that, is 0.5. So -7.5 plus 0.5 gives you the new y-coordinate of -7. And we take that. And again, increase the x coordinate by the step size. 2 plus 1.5 is 3.5. And the new y coordinate we just got is negative. And we know to stop for a couple different reasons. One is we're stopping at 3.5, which is exactly what we're asked to approximate it at. That's one way you can tell. And another way you can tell is that it says 3 steps. We've gone through the process 1, 2, 3 times. Each one of these horizontal procedures here represents 1 step. So that's another way you can tell. Both of those should correspond. So we can say our final answer here, h of 3.5 is approximately negative. All right, let's take a look at the next one here. So this one says, consider the logistic differential equation. We'll talk about those later on in the school year. But for now, we're going to use them using Euler's method. We'll come back to what other things you can figure out with those special types of differential equations later on. And it says let y equal f of t. So we've got t here instead of x. The particular solution to the differential equation with f of 0 is 6. So oftentimes this is referred to as the initial condition. Here they just give it to you. So we have 0.06. But notice in this problem there's no x. Instead we've got t. dy dt, you can see f of t. So it would be t and then y instead of x. And then it says to use Euler's method, starting at t equals 0 with 2 steps of equal size to approximate f of 1. So again, to get our step size, in this case, though, it's going to be delta t. We'll take the difference of where we're starting, where we're trying to approximate 1, minus where we're starting at is at 0, divided by the number of steps is 2. In this case, our step size is just 1/2. So now we can start with a point which is 0.6. And then calculate the slope, in this case, dy dt. Sometimes it takes a little more work. The table ones are the easiest because you can tell the derivative values right away. Here we actually have to substitute in. Now what's different about it, normally our derivative has x in it, or sometimes x and y. Here, there's no x, you have t, but there's no t in the derivative, only y. So we're only going to be substituting the y coordinate of 6 into the derivative. So that'll give us 6 divided by 2 times 8 minus 6. And then we can simplify it. 6 divided by 2 is 3. And 8 minus 6 is 2. So we get our derivative is 6. And again, we multiply that by the step size, which here is delta t, which is 1/2. So once you get the value of the derivative, you multiply by the step size to get your change in y coordinate. In this case, the change in y. Or you could call it the change in f, since y is the same as f here either way. Is 6 times 1/2 is 3. And then we add the original y coordinate, which here was 6, to get our new y coordinate. 3 plus 6 gives you 9. Okay, so that's one step. Now let's go through that process one more time. So here we increase the, in this case, t coordinate by the step size, which is 1/2. The next point would be 1/2. And our new y coordinate was 9. So now we have to substitute in the y coordinate into the derivative. So it'd be 9 over 20 times 8 minus 9 gives you 9 over 2 times negative 1. So you get a derivative at this point of negative 9 over 2. Our derivative or slope. Again, we multiply it by the step size, which is 1/2. Gives you negative 9/4 is the change in our y coordinate. And then you add the original y coordinate, which was 9. However, since it's already a fraction, it's probably easiest if we get a common number of 4. So if you multiply the 9 over 1 by 4 over 4, 9 is the same as 36 divided by 4, 36 fourths. Then you can add it to the negative 9 fourths. to get positive 27 fourths. The y-coordinate. And that to the point. Increase the x-coordinate, in this case t-coordinate, by the step size. 1/2 plus 1/2 gives you 1. And our new y-coordinate is 27 fourths. And again, we stop right there because of two reasons. It said 2 steps. We've gone through 2 steps here. And we're trying to approximate f of 1, and that's where we have f of 1. So, all right, here the f of 1 is approximately let's take a look at the next one here. So this one says the number of frogs living in a pond at time t is modeled by the function y equals f of t. This is another logistic differential equation. It's just an applied version one. And it says t is measured in weeks. The number of frogs at time 0 is f of 0 equals b, where b is a positive. Here, rather than giving us a specific number here, they're telling us it's just some positive amount of frogs that we should calculate. And then it's also telling you for y is greater than 50, the second derivative is less than 0. For y is less than 50, the second derivative is greater than 0. We'll see later on the problem. Okay. So for part A, it says let b equal 20. Okay. So now we're going to put in a specific number for this b value. So that's telling you f of 0 equals 20, which means you have the point 0, 20 on the function f, which represents the number of frogs in the pond. In this case, again, we don't have x, we've got t. You can see it's dy dt. And we have y, or you could call it capital F if you want, since y equals f. Probably easier to just leave it as y. And then what we're trying to do is use Euler's method again, with starting at t equals 0 with 2 steps of equal size to approximate f of 4. So again, to calculate the step size, delta t in this case, you take the difference between where you're trying to approximate 4 and where you're starting at 0. That's the gap between the 2 points, where you're starting and where you're approximating, and then divide it by the number of steps, 2, to get the step size. So in this case, 4 divided by 2 is 2. So our step size is 2. And let's go through the process of Euler's method now. So we're starting at is 0, 20. And then our derivative dy dt is given right here. So again, we have to do some calculations on this one. So if we substitute in 20, we'll have 1 over 160 times 20 times 100 minus. Let's go ahead and simplify that. Notice 20 over 160, you can first reduce the zeros. So it's 2/16, but that reduces to 1/8. And then 100 minus 20 is 80. And then 8 goes into 80 10 times, 1/8 of 80. So we get derivative of 10. And then you multiply that by the step size delta 2, which I figured out was 2. To get the change in the y-coordinate, in this case the change in the number of frogs, is 20. Plus the original y-coordinate also happened to be 20. Gives you a new y-coordinate of 40. In this case, we're estimating that after 2 weeks, the number of frogs has doubled from 20 down to 40. So that's one step. Now let's go through another step. Okay, so this time, again, the t-coordinate increases by the step size, which is 2. So 0 plus 2 is 2, and then the new y-coordinate we just estimated is 40. And again, our derivative just uses y, it doesn't use t at all. So we'd have 1 times the y-coordinate now is 40, and then 100 minus 40. So this time again, zeros reduce out here, so you get 4/16, but that reduces to 1/4. 100 minus 40 is 60, and 1/4 is 60. 4 goes into 60 15 times. So we get our slope at this point is 15. again, times the step size of 2 gives us a change in y of 30 plus the original y coordinate at this point was 40. The new y coordinate would be 7. And then we increase the t coordinate by the step size, so 2 plus 2 gives you 4. New y coordinate 70, and again, that's where we stop because we're approximating f of 4, so we have that. And we've gone through 2 steps, which is what it said. So both of those show us that we're done. So f of 4, the number of frogs after 4 weeks is approximately 70 frogs. All right. Now let's take a look at part B. This is asking something a little different. It says determine whether the approximation found in part A, the 70 frogs, is an underestimate or an overestimate for the number of frogs in the pond at 4 weeks when b equals 20, which is what we started with right there. Explain your reasoning. So remember, Euler's method is really just like using multiple tangent lines rather than just a single tangent line to approximate a function, which is why it tends to give you a little better approximation than just local linear approximation where you're using this, just one tangent line. And it also allows you to approximate further away from the point of tangency, whereas the tangent line, if you go too far away from the point of tangency, it tends not to be a very good approximation. Notice with Euler's method, it went from 0 all the way to 4. You typically wouldn't do that on just a local linear approximation, go that far away. But Euler's method, you can kind of go as far as you want. And the more steps you use, the more accurate your approximation tends to be. So now, just like the local linear approximation, since we're using tangent lines, it comes down to looking at the second derivative. And notice in this case, we have two different aspects of the second derivative. When y is greater than 50, the second derivative is less than 0. When y is less than 50, the second derivative is greater than 0. So to figure out which of those we end up using, you just have to think, well, look at the 2 points we found the slopes at, 20 and 40. And both of those are less than 50. So you say y is less than 50. And remember up here it said when y is less than 50, the second derivative is greater than 0. And when the second derivative is greater than 0, remember that means the graph is concave up, shaped like a cup. So again, if we just sketch a picture of that, something concave up, shaped like a cup, and like you do for the tangent line, because we're just using multiple tangent lines, you can see that just like the tangent line approximation, even though it'd be more accurate than just a single tangent line, most likely it's still going to underestimate or under approximate the actual value because of the concavity. So that's what we can say. We can say, in this case, our answer was underestimates the number of frogs in the pond. Just using the same word here, just turning into a statement. At 4 weeks. And your justification would just be since our second derivative here, since, whoops, since our second derivative, d squared y dt squared, is greater than 0. And then you want to specify that it's not always greater than 0 in this case when y is less than 50. And notice even though our answer was greater than 50, 70, what we used to estimate to end up getting that 70 was the 2 points 20 and 40 where the y coordinate was less than 50. So that's where we found the tangent lines at. So you're not looking at your final answer to see if that's greater than or less than 50. You're looking at the points you actually used when approximating to get that answer. Okay, let's take a look at one more problem here for the Euler's method. This one's a little different and involves something we went over last school year in AP Calc AB. However, we haven't reviewed it yet this year, but it's a little refresher before we get to that in the next chapter. So it says use that g of x equal this definite integral here using Euler's method. Starting at x equals 1 with 2 steps of equal size to approximate g of 5. So notice, unlike most of the problems, it actually doesn't tell us what g of 5, what the starting point is. At 1, we know starting at 1, so you actually have to find the starting point here, g of 1. So that means you plug in the 1, notice just for x, right, not for t. So go from 1, we plug in the 1 right there for x, of the square root of 1 plus 8t squared. But remember, when the lower and upper limit's the same of a definite integral, it's just going to give you 0. Okay, so our starting point here is actually 1, 0. Here's just x and y. And then we're using 2 steps of equal size to just calculate our step size delta x. We're going to take 5 minus 1, where we're approximating minus where we're starting, and divided by the number of steps is 2. Gives you 4 divided by 2, which is 2. So our step size is 2. Okay. And now we can go about figuring this out. So our starting point here is 1, 0. And g prime of x is what we need next. Notice we haven't figured that out yet. So let's do this. I'm going to use our space down here to find g prime of x. And this is a review from something we did last year. So remember, when you're taking the derivative of an integral, you initially write it like this: d over dx with brackets around it. Integral from 1 to x, square root 1 plus 8t squared times dt. So remember, this is the second fundamental theorem of calculus. Remember, derivatives and integrals are reverse operations. They're, or you could say inverse operations. They reverse each other. And so this one fits it exactly because the lower limit's a constant and the upper limit is just x. So remember, since they reverse each other, they kind of essentially cancel each other out. The only thing that changes is this variable x replaces this variable t. So g prime of x, which we're using right now, is just going to be the square root of 1 plus 8x squared. So that, otherwise, the function doesn't change except for the x replaces t. So now we can use that to plug in our x coordinate of 1. So this would be the square root of 1 plus 8 times 1 squared. So we get square root of 9, which is 3. So that's our derivative, 3. And then we figured out the step size. Delta x is 2, so 3 times 2 gives you a y coordinate of 6. Change in y coordinate of 6. But that's actually the y coordinate also because we add the original y coordinate to 0 to get our new y coordinate of we take that new y coordinate, change the x coordinate by the step size, so now it's going to be 3, and the new y coordinate is 6, we just found right there. And now if we substitute into that, we get 1 plus 8 times our x coordinate there is 3, so 3 squared. So here we get 3 squared, 9 times 8, 72 plus 1 is 73, which in this case is not a perfect square. That's good. And then multiply that, I don't think there's anything to pull out there, by 2. The change in the y coordinate of 2 root 73. And then the original y coordinate was 6, so plus 6 is going to give us our new y coordinate of 2 root 73 plus 6. Where does that look? So that's our new y coordinate. And then increase the x coordinate by the step size 2, so 3 plus 2 gives you 5. Oops. And the y coordinate we just found is 2 root 73 plus 6. And again, that's where we stopped because we went through 2 steps and we were trying to approximate g of 5. So now we can say g of 5 is approximately 2 root 73 over 6, or 73 plus 6. So they don't always work out nicely, your answers there. Sometimes they do, sometimes they don't. All right, that concludes the notes for AP Calculus on the topic of Euler's method continued.